welcome to CPEdict. In this video we are going to solve the last problem from the August LeetCoding challenge, and it is a very popular problem. You might already be knowing the solution, but let's proceed with our video. It is called delete node in BST, that is binary search tree. So we have been given a BST rooted at some node and some key. So we need to delete the node which contains that particular key. It has two steps. First we need to search that node, and if that node is present in our BST, then we need to delete it. Time complexity should be equal to the height of the tree. Let's see, we have this binary search tree, and if you want to delete 3, then after deletion the tree would look something like this. That is, after deletion the tree all the nodes should be following the property of BST. There can be different arrangements after deletion. Any one possible arrangement will do the job for us. Let's see how we can solve this problem. So we have a BST. Let's draw it first. Okay, suppose this is a BST. Now we want to delete a node containing the value k. There can be 3 cases. That node which contains the value k can be a leaf node, or it can be an internal node which has only one child, or it can be an internal node which has two children, that is both the children, the left and the right one. So for the first case, suppose we want to delete this leaf. What we simply can do is just put null to the left of this node. That is, so we want to delete this node. We will just say that suppose this is node n, we will do the left of n is equal to null. Now for the second case, when the internal node is having only one child, let's take an example. Suppose we want to delete this node, and it is having only one child. Then what we can do, we can put the pointer of its parent and point it to that node, as we want to delete this node. What we will do in this case, we will do, suppose this is node r and this is x, we will do the right of r is equal to x. It will delete this node in between. Now let us come to the last case, which is the important one, when we want to delete a node which contains both the children. Okay, so let's say we wanna delete this node as it is having both the children. Now the most popular approach which is used generally is, we find out the in order, and either we look for the largest, or the largest value on this left subtree of this node, and suppose this is the largest value we are having in this left subtree of this particular node which we want to delete. What we will do, we will delete this and put the value which was present at this node and put it here. This is one thing we can do, or we will look for the smallest value on the right subtree. That is, we will look for this subtree and find a node which is containing the smallest value among all the values present in this subtree. Suppose it is present somewhere here, then we will delete this node, and the value which was present at this node, we will just take it and place it here. So in a way we have deleted this node. And to find the least value, the minimum value on some particular BST, we just need to find out the leftmost node on that BST. And to find out the largest value in BST, we need to find out the rightmost node. As if I am assuming you are aware with the properties of BST, which you are, or suppose we have these three nodes in a BST, then the value, and it contains the value x, then all the nodes on this subtree will contain the value less than equal to x, and all the nodes on this side will contain the value greater than x. Okay, so the most popular approach is this one, but we would be using a different approach just for fun. Let me draw another BST for that. Yep, and suppose we want to delete this node. What I did was I checked whether the right of this node is empty or not, is null or not, like the right of this node. If the right of this node, which is the left child of the node which we want to delete. So I checked this node and I see if the right of this is null, then what I simply did is I put the right pointer and here to the right of the node which we wanted to delete earlier, and the left of this node I have changed to this value. So in a way we have deleted this node. This is one thing we can do. So this was the first step and this was the second step. Okay, and in another case I checked whether the left of this node is empty or not. If the left of this node was empty, what I did I put the left of this node as this one and change the left of this to this. This will work as we are sure that all the values present in the subtree, suppose it contains a value x, is greater than x. So if I put this node at this point, and then it will also mean all the values present in this subtree would be lesser than x. So it will follow the property of BST. Now this was the two cases, and there can be one last case which we need to consider. Yep. So suppose we want to delete this node and we see that even this is having both the left and right childs. So what I did was I picked up, let's create a better tree. Yep. So as we want to delete this node which is colored in red, so I picked up this whole subtree. Okay, and I have the reference of this node. Let's say I am storing it in some value, call it root, and the value present here is well. I picked up this whole subtree using this only one pointer. This pointer will help me represent the whole subtree. I picked it up and then I tried to insert it. On this binary search tree. I compared all the values to this well, and I traversed this whole subtree. And when I was able to reach the leaf node, or the node which is not present, suppose we have come to this point and I see there is no nodes remaining at this point. So I just put the reference of this and point it to here. So I was kind of inserting a binary search tree into a binary search tree. I hope you got the point. And then after that I just change the left of this parent node to this. Yep, I hope you got the point. So let me explain it once again. What we wanted to delete the node which is colored in red, So what I did, I picked up the whole left subtree and I tried to insert it on right subtree of this node. And by inserting, I was just comparing the value present on the root of this left subtree. I assumed it is val, and the pointer was root. So I kept traversing the right subtree till the point I am able to reach the end of BST. And suppose I reached the end of BST at somewhere here. I found it is null at the left of this node is null, and the value present, suppose it has a value v and it has a value v3. The value which was there at the root of this value, which was val, if val is greater than v3 and val is less than v2, then we would be putting the whole left subtree here. So yep, now this is a different approach. There is one disadvantage to this approach, which is it will increase the size of our binary search tree. So if we are having more computations after this process, it will kind of reduce the time complexities of further algorithms or processes. So I just tried a different approach. The efficient one would be the one which I explained earlier, to find out the in-order predecessor or in-order successor. Yep, let's see the code for this part. It is a lengthy one, sorry for that. So I wrote many helper functions in this. Yep, this is the main function which we need to create or build. First of all, yep, I am maintaining two global variables, the two global pointers, that are node and parent. If I am able to find such node which is containing the value key, I am storing its pointer in node, and the parent of that node, I am storing its address in parent pointer. And there is side. Side basically tells us, while we are going through our BST, yep, suppose we are going through our BST and we want to delete this node. The side basically tells us which side this node is currently at to its parent. Suppose as it's a left child of its parent, then the value of side would be 0. And suppose if we had wanted to delete this node in blue, then this is the node which is the right child of its parent. So in this case the value of side would be 1. So side basically just tells me which side this currently node is currently at with respect to its parent. Okay, and there is one function is leaf, which basically just tells me whether this node is a leaf node or not. Yep, so initially I have marked them as null and side as 0. Then I called the find function, which updates the value of node and parent. And if we are not able to find any such node containing the value key, we see that node is still null, because node contains the pointer to the node we want to delete. And if it is null, it means we weren't able to find that node. Let's see the code for find function. Yep, I see if it is if we have reached to the end of BST, or either we have already found the node. As it is not null, we just return. We see if the value is equal to that the key which we want to search. We updated the parent, the node, the side and return from this function call. Otherwise we call the same function recursively on its left child, on its right child. We see, yep, if parent is null, yeah, if we have crossed this point, it means we found the key. That is, if the key is not found, we will simply return root from this point. But if we are reached to this point, it means we have found the key. And if you see the parent is null, it means the key which we found, its parent is null. It means it must be in the root. So I called another helper function which is delete root. Let's see the delete root. I checked whether it's leaf or not. If the root is itself a leaf, it means there is only one node in our BST. Then I return null, and I checked if either one of the children of root is null. Then I just return the other subtree. For example, I want to delete this node, and I see its right children is null. I just return this node. And suppose in other case I have this binary search tree and I want to delete this node, then I just return this node, the right child of root. Otherwise, if I am not able to find such any empty children and empty pointers, it means the root is having both the children. Then I called the helper function delete both children. I will explain this function later. Let's see the other part. Let's see if we have reached to this point, it means it is not the root which we want to delete. Then I called another helper function which is called delete internal node. Let's see what it is. I checked if it is leaf. It is leaf. I just put the parent's pointer. I just changed the parent's pointer as null. I first checked side. Suppose is the value of side is 0, then it means it must be in the left child of its parent. Then I did the parent left equal to null. Otherwise, if side is 1, it means it must be in the right child of its parent. Then I put parent right equals 1. I returned. Then I checked whether the node which you want to delete has only one child or not. If it has only one child, suppose we want to delete this node. If it has only one child, then I just change the parent's pointer and update its value to this and let it point to its children. Let it points to the children of the node which we want to delete. I hope you got the point. And if we have reached to this point here, it means the node which you want to delete is having both the children. Now I am called my helper function delete with both children. The node, if it means this node is having both the children which we want to delete. Now it is the same helper function which I had called in the delete root function here. So this is the last thing which I need to explain. It is, yep, where it is, delete with both children. Yep, here it is. So what I did here is, yep, I inserted the left subtree into, I inserted the left subtree into the right subtree, and the value present at the root of left subtree is this. Now let's see the last function, the insert one, where it inserts the BST rooted at new node to BST rooted at current node, which I was talking about, and the root of this new node BST contains the value val. So I saw if the value present at the new nodes, if the value present at the root of new node BST is lesser than the current value, like the current node's value, and I also saw the left of current is null, it means I need to place this subtree at the left of it. For example, I have reached to this point, its value is v, and we see val is less than v, but the left of v is null. Then I just updated the left of v and let it point at that subtree which I want to insert. Then I checked the other way around. I checked whether if the value is greater than val, if the value is greater than the current node's value and the right is null. For example, I checked here, let's say we are inserting here, it contains a value v and val is greater than v, but the right is null. Here the right is null, and I just change the right of this point node and let it point to the subtree which I want to insert. And if we have crossed to this point, then I'm moving ahead or going deeper into my BST. I saw if the value is lesser, and I call the same function on its left subtree. If the value is greater, otherwise I call the same function on its right subtree. This is the insert function, and at the end I am returning the root right. Why I am returning the root right? Let me explain that. Yeah, so I wanted to delete this node. What I did, I picked up this whole subtree and inserted it inside this subtree, the right one. And at the end, I do not care about this part. I just return this node. And what it is the right of root, as this was the root initially which I want to delete. So that is why I have written root right of root here. I know this is a pretty lengthy code, but I just did it for fun, as it was very cliche. The normal code which we use to find out the in-order predecessor or in-order successor, it was a very cliche code, so I tried to do it using some another way. I'm not sure whether I would be having too many viewers at this time, as it is a very long video, as I can see. So yep, I hope you like the video, and if you like our videos, then please like and do subscribe to our channel. This was the last problem from August LeetCoding challenge. From tomorrow onwards we would be solving the problems from September's LeetCoding challenge. So see you there, and till next time, take care, sayonara.